Hello, I'm Cameron, and this is my friend Carl.
Hello, I'm Cal, and we're at the Microrobotics lab at the University of Sheffield. What do we do at the lab, Cameron?
So we make really small robots with the aim to put them in inaccessible places. So what we do is we call them microrobots, and we control them using magnetic fields. So magnetic fields are really useful because they can pass through most materials, including things like the human body, the table, everything. So we can have the robot in somewhere while controlling it from outside with a magnetic field.
Yeah. And magnetic field being able to pass through anything is particularly good in medical robotics, which is where our focus lies in, because unlike radiation sources like X-ray, we can use magnetism to control our robots without any harm to the patient. And that's what makes it particularly useful in this field. So, Cameron, can you show us your first demo?
So the first robot we're going to show you, it has a little wireless motor inside it. So this has two magnets facing opposite directions, so one up and one down. And when we apply a magnetic field to it, using this coil we've got here, it pushes one of the magnets upwards and one of them downwards. And then we can reverse it so that we swap the current, instead of going that way, it goes that way around the coil. And then the magnetic field goes down instead of up. So that then rocks the other way. When then in the middle here, we have this little ratchet mechanism that means from the rocking motion, we get rotation of the wheel. So we're now just going to demonstrate that with 3 of these robots on our coil.
So our lab in particular, we focus on regenerative robots. These
That's not working.
In particular, the gas.
There we go. So what you can see here is the magnetic field is alternating upwards and downwards, and it's pushing on these magnets, and it normally moves the robots. Like this one here is demonstrating. Turning the wheels and meaning it moves. Obviously, it can't go outside this circle because our coil's only this big. And if it goes off, the magnetic field's facing the wrong way and the robot falls over. So I'm just going to stop that there. And Khan is going to demonstrate a second robot to you.
Right. Hello again. Yeah.
And if I put down on the joystick, you'll see is the liquid starts being pumped into our
Right.
And then the bubble will be covered. We can really start seeing them.
Okay. So here you can see one of our origami robots. This is our conductive model. And this one can move along in any direction because we have 4 more coils in the corners, like this one, and in each corner. And using the combination of them, we can use them to direction the robots anywhere we want them to be. And this particular origami robot is chosen to be this way just so that it can be folded into a pill and then released inside the body so it can perform surgeries. And here I'm going to demonstrate the movement it makes. You can see that you can control where it moves. Of course, again, you have to be within the perimeter of the robot. And as you can see, it can also pass through the body as well, quite comfortably. And it can move up and down slopes as well. It's having a bit of a rough time today. Oh, yeah. Basically, you get the idea that you can control them. Right. So we also have another mode where here's a cube magnet. It's nothing special, just a cube. But you can control its direction, same as the origami robot. So it can roll through the direction you want it to be. And here's a model of an intestine. Let's imagine that this robot is inside the intestine, and we're going to perform or maybe reach a cancer cell here to take some samples. So you can use the controller to navigate. But I also have one more demo to show. We'll need some setting up to do.
Tissue is alive, so it can actually grow, but it takes weeks to do it. So imagine you are pulling on the tissue. It starts proliferating, and you get.
Okay. It is set up right now. So here's the plot twist. You should be able to control this robot as well. If you type in the chat up, down, left, or right, you should be able to control the robot too. Just in the live YouTube comment chat. I'll also participate, just to prove the point. If you just type right.
So you can imagine tissue is like
there you go.
So imagine you have a spring with you. You start pulling on the spring. The spring elongates at first, but then it gets harder and harder to elongate more. That behavior is called stiffness, and the tissue is like a spring. You can think about tissue as a complex set of springs. And we developed our one model, which is called with soft tissue simulator, that is capable of replicating the springiness of soft tissue. So it will help me to illustrate the platform now. We have a bottom plate that's fixed in place, and then we have a top plate that moves up and down based on interaction with our robotic implant. So the robotic implant is placed there in the middle, you can see.
Anyway, and you can also type the commands or ask your questions right now, so we can go to the Q&A phase. So if you have any questions, fire them up.
One group, the US, developed.
Right. So how the robots are made. So
we've got two different types of robot here. So I'll start by talking about my robot. So I'll just put this under the camera for you to see. So there's a few different things going on in this robot. It shouldn't have that many magnets. There's quite a few extra. So we use a mix of properties. The wheel's made of acrylic plastic, so that's laser cut. So we have a high-powered laser that's controlled with some motors to really accurately position it, so we can do some cut those out for high precision. In the middle, we've got some 3D parts. So the gears and everything are 3D printed with a process called lithography. So that's where we get resin that cures with UV light, and we have a computer-controlled UV light that scans across and cures the resin in specific places, so we get accurately formed 3D parts. So that's how we make these. My plan's going to talk about how we make the origami robots.
Right. So this specific model of origami robot we have here has 3 layers folded over together. But first, it's laser cut or made by hand, depending on the model. And it's made of the 3 main layers. Made of is the first one is PVC. It's a thin, transparent sheet of it, and there is double-sided tape, a very strong one, holding between the second and the first layer. And the third layer is a sheet called Duralar, and that's conductive, like this specific model. But we have 2 other models as well. One of them, which is disintegratable. One of them disintegrates inside water, and the other disintegrates inside an acetone. Yeah, basically that.
So don't forget, if you've got any, you can pop them down in the chat comments below, and we'll pop those up on the screen and answer them. Nothing. How are we expecting to perform an operation in the future with an origami robot? I can answer that one, Khan.
Yeah, I'll go with it. So basically, this specific robot that we designed is not meant to be used inside the body, but we have other models which can reach anywhere inside the gastrointestinal tract. So you can fold this into a pill, and the patient swallows the pill, and it can reach anywhere within the digestive tract. So, for example, if there were, let's say, detection of cancer cells in the intestines, of course, the current method we use require a colonoscopy, which is quite detrimental to the patient. It's not a pleasant operation. So if you had an origami robot inside a pill, that would go down and either detect where the cancer cells are, or maybe take samples from them, maybe even remove them. So that's like one of the issues we can solve. Another could be stomach ulcers and touching them. So that will be in an acidic environment. We have another model of origami robot that kind of folds and opens up and patches over the stomach wound, applying medicine in one of its layers while it's disintegrating.
One thing you may be able to appreciate is the fact that our robot has like through the various layers. So that means
we have one more.
So we've got a question from Dana. Can you send more of these robots inside the body at the same time? So I think I'll take this one.
Sure.
So when we're using the 4 coils to create a very accurately directioned magnetic field with the style of robot that Khan demonstrated, it means that all of the robots behave in exactly the same way because they experience the same magnetic field. Whereas with the type of robot I demonstrated, using the very simple up and down magnetic field, it means we can have multiple robots at the same time. And yes, it'll drive at the same time, but they can all be heading in different directions. So this is something we're very ongoing and we're working on, is to have multiple robots at once in the same place. So that's some current and exciting research for you, Dana.
describing like pulling and releasing the tissue like periodically, but you experience that with just particle.
We have another question. Can you navigate in a 3D space?
That's a difficult question. So the first robot we demonstrated, that relies on being that has the magnet sort of sitting here. So that sort of only really works on a plane. So it can go anywhere within the 2D plane, but we can't sort of control it. We can't tip it up on its end, so we can't be truly 3D. It could like drive up a ramp so it's in a 3D sort of terrain, then it could navigate that, but it couldn't do free movement in 3D. There are magnetic robots which can operate in 3D, so things like spinning propellers, things like that, which can be controlled by magnetic fields and navigate in 3D space. Do you have anything to add, Khan?
Well, the robot can move up slopes, but I think that's a limitation that you can use it for navigation, but not truly 3D.
So I hope that answers your question.
Here's the soft robot. You want some sort of behavior there.
From which distances can you use it?
Should we get a ruler and test it?
Maybe.
It sounds like we can do some live science on air.
Yeah. It will be determined by the magnetic field created by the coils. And over distance, of course, this magnetic field reduces. However, the area that we use dedicated for operation is supposed to be so that it can be used inside people.
So the top of this surface is about 5 centimeters from our coils. So we know we can do that. We'll see how much higher we can go for Kibis. Sorry. So, are you operating? One of us actually broke the robot, wouldn't it?
Yeah, we'll make the other one. Oh, sorry, drop something. There we go. That's an operation. Yeah.
There we go. So we're working at 5 centimeters. We'll go up another 2, so we're at 7 centimeters. I don't know where.
Oh, I put it down. Maybe it's the
No, the coil's not working.
Oh, the cables are off.
Right, we've broken it. We're going to reset the coil. So we're just turning it off and on again, like you would do with any computer.
Yeah, it always happens.
Start university.
There we go.
Okay.
So
Yeah.
we fix the system by turning it off and on again. We'll have another go at 7 centimeters.
There you go.
Works at 7.
Yeah. Still the top.
Should we go? We'll go up to
10. Yeah.
that's working at 15.
That's too much of a slope to do
So
at a distance.
it just about works at 20 centimeters plus the coil.
Although actually, if we increase the current multiplier, I think we can go higher.
Yeah, so we're only
Because-
using 5 amps.
Yeah, we can go a lot higher, but it's just so that we can use the system in longer term. So in a short distance, we might be able to, but the coils will get too hot if you do it at a much higher current rate. Then another one. Nice.
What are the advantages? So we've got a question from Donna D again. What are the advantages of origami robots or micro robots for bioengineering? That's a big question, isn't it, Carl?
It is a big question.
Would you like to start or shall I?
Well, it's an entire field, so it might take 2 of us to answer.
Right. So I'll start. So we sort of touched on this when we were talking before. So there's a lot of things currently that involve surgery, so, that we hope to be able to replace by using a micro robot that you swallow. Instead of anesthetizing someone and cutting them open, the aim is to be able to just put a small robot inside them to then solve the problem and then pass out again without having any surgery or any of the side effects of that. If any of you are really keen, you can go and watch the film Fantastic Voyage. It's an excellent example of this. Carl, do you want to answer about the origami robot side of the
Well,
question?
of course, but just micro robots in general would be very useful in bioengineering, because in bioengineering, you will be working with very small stuff that would need to carry some load and would require control. So I think that would be a big advantage of using generally all origami robots and micro robots in a field like bioengineering.
Yeah. And the aim of the origami robots is to be able to pass down a sort of relatively large robot in a really small space to then unfold it to a fully functional robot. So this is already being used in space. So there's sections of the International Space Station that are origami. So it can fit it into a small rocket, launch it up, and then unfold it to a full space station module. So our aim is to achieve sort of the same thing, but on a smaller scale, with a capsule swallowing it into the body instead of launching it up into space.
Talk about the space applications. Origami structures are also used in solar panels. So when they fire them off, they can capture the maximum amount of space in the smallest amount of space that you can send it with.
I think that answers the question.
Yeah. Well, the second doesn't even the question. I'm just
So I think we're at this 25 past there, so we're out of
about
time.
Time to wrap up.
We'll be going live again at past for another demo.
Thank you for watching.
So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. Music.
Right. Let's go.
Hello, I'm Cameron, and this is my friend Carl.
Hello, I'm Khan, and we are at the Microrobotics lab at the University of Sheffield. What do we do in this lab, Cam?
So we do microrobotics. So micro means it's really small, sort of on the micrometer scale and bigger. So our main focus is on the centimeter scale, with the aim to make them even smaller. We control our robots using magnetic fields. The reason we use magnetic fields is because they can pass through most materials, such as the table, the chair, the human body. This means we can put our robots in really inaccessible places that we couldn't get a cable through to or any other control method, and just control them from the outside with a magnetic field.
Yeah, and the biggest advantage of using magnetic fields is in the medical sector, because magnetic fields are not harmful to the body, and it can pass through anything, including our own body. And unlike X-ray radiation, we can use magnetic fields, again, without harm to the body, and also use sensors to spot where our robot would be. And this gives us the advantage of using them in medical fields.
So I'm going to demonstrate a robot to you. The first thing I'm going to show you what this big red thing in front of us is. So this is what we call a coil system. So in here, we've got electromagnetic coils. So this has a few hundred turns of wire around it and is connected to an electrical power supply. So we can send the current either clockwise or anti-clockwise round this. And that gives us a magnetic field that either goes upwards or downwards. And we can use that to control our robots. So here is one of the robots I'm going to show you. So this has magnets on either side of it, facing in opposite directions. So one side they're facing upwards and one side they're facing downwards. This means when it receives a magnetic field from underneath, this lever in the middle tilts and it rocks. And then when we reverse the tilt, it goes downwards, it then rocks back again. That then goes to a ratchet mechanism which controls these wheels and makes them go forwards. It's a bit like if you're sat on your bike and you just pedal forwards a little bit and then backwards a little bit and then forwards a little bit. You just go forward sort of slowly. So I've got 3 of them here that I'm going to show you.
What we get is that we get robots that grow, they call this twist and sort of bend.
So the idea behind some robots
So we can see now the magnetic field, I've set it quite strong, and we can see that it makes this lever in the middle rock back and forwards, and that makes the robot move across the work surface. When they get too close to the edge, like these ones, they don't work anymore because that's where the magnetic field is positioned. So these ones don't have magnetic fields to make them work. Whereas this one in the middle, we can see it does, so it's moving around quite happily. That one doesn't work well. So I'm just going to stop that there and let Khan demonstrate the second robots to you.
Right. Hello again. So I'm going to be demonstrating an origami robot right now. After I do the setup, of course. Right. Okay. Right. So here is our origami robot. And you can see the tiny magnets on top of it, which is used to control the robot. And this by itself is not the robot, of course, because the rest of the coil system also counts as part of the robot, because we have these 4 extra coils in each corner, which lets us control the robot in different directions. So we can navigate the robot, let's say, inside the body. And that's also one particular reason why we use origami robots, because they can bend into different shapes and also into smaller shapes, particularly, and fit inside a pill. This gives us the advantage of being able to reach anywhere inside the body, inside the gastrointestinal tract. And you can see that the advantage of this robot is that no electronics are needed to be on board to control it. And you can see that it can be controlled in any direction, really. If it doesn't go off the, yeah, there you go. So right now I'm controlling it with the analog stick of the microcontroller I've connected. And you can see it move around in the direction I push it into. And it can also pass through the body, as I mentioned, as you can see. It's having a bit of a trouble. Why? There you go. I think my hand is a bit too slow. But basically, it does pass through the body. Yeah.
And the second example is short pulse syndrome. In this case, what happens is you see all this black space in
anyways, you get the point. So one other mode I want to show is here's just a small cube magnet that I can move to any direction. And let's imagine this is connected to our robot that's going to perform an operation. And here's an intestine model that we are going to navigate through. And you can see that we can easily just navigate through this 2D space. And let's say we have some cancer cells we want to reach here. And we can just go and, I don't know, collect our samples there, maybe. But that basically just completes an operation. But we have one more thing to show off. Setting up. We'll be back in a sec.
And obviously these sort of tests take a lot of time and it would require.
So the last thing I would want to show off is you can also control the robot right now. Imagine you're in another operating room, you are the surgeon, and you are navigating this origami robot from someplace else, let's say. And just to prove the point, you can type left, let's say, and it will go left.
What we want to do in our lab is also try and see if there's a potential way around it. So to see if we can actually.
Can I turn it off? Oh, there you go. Yeah. There's some input lag. Of course, it's on live stream, so it will be a bit late, of course. But yeah.
So just pop these directions up, down, left or right in the comments below the live stream, and you can control the robot yourself from home.
It's harder and harder.
There we go. That's great. Yes.
And you can think soft tissue has a similar property. Actually, you could think of soft tissue as a complex arrangement of springs. Now,
and also while you do that, you are also able to ask your questions right now in the chat, along with the commands if you want to continue that. They are both functional at the same time. So if you have any questions, please ask them right now. We have about 10 minutes to answer them. Right. So we have one question. How are you expecting to perform an operation in the future with an origami robot? Right. So as I mentioned, let's just go with the intestine example that I've given. Let's say you put your origami robot inside a capsule and you swallowed it. And let's say you're trying to diagnose a patient for intestinal cancer. The first method, the main method used today, is through colonoscopy, which is a very, very uncomfortable experience for the patients themselves. So using a microrobot inside the body to detect if a cancer cell is present is possible, or maybe collect some samples for testing is also possible, or maybe even perform surgery and remove the cancer cells at the point. So in a perfect future, it would be even able to do this maybe automatically. So you just swallow the pill and it sorts itself out. No more cancer.
very, very long trials is fault tolerance and safety. In particular, we need to see.
So, question from Simon Goldsmith. They are very small. Have you ever lost one? I think if you emptied out the container on our vacuum cleaner, you'd find about 10 micro robots in there that I've lost. I don't know about anyone else, but I think most of mine are in the vacuum cleaner.
Yeah, the smaller they go, the more we start losing.
So we've got a question from Shuhei. Can we navigate in 3D space? So I think I'll answer that about my robots, and Khan can answer his. So let's put that in view of the camera. So my robots, the one I showed at the beginning, they rely on having that horizontal magnet. So they mainly move around on one plane that's sort of perpendicular to the magnet. They can drive anywhere on that plane, and they could drive up ramps and stuff. So if there's 3D features within the environment, they can negotiate that. But we couldn't navigate it anywhere within three-dimensional space.
Right. And with the origami robot, it can climb up a slope. However, it will never be truly 3D. It will only be able to go up, down in the navigation we use, because the navigation is designed to be on this, well, not specifically on the platform, but in the area of the platform. But yeah.
There are some micro robots that we have been looking at in our group, such as things like propellers that can move up and down within a fluid and propel themselves within that environment. But the ones we've demonstrated here today, not really truly 3D space.
We have one very related question to the space one. Can magnet and patient be moved also to position 3D in the robot? Possibly, maybe the patient could be turned upside down if needed, if it's having trouble going over a certain part of the body. It is possible, but instead of the magnet already moves inside the body, but if the coil system was also able to move, it would be able to do 3D space movements. So if you had this whole structure on like a spinning mechanism, you will be able to use it in other directions too.
I've certainly done experiments where I've needed to turn the coils to get things in another direction. The other thing is, within the patient, you also have peristalsis, which is a process of moving food through the intestinal tract, which would also help an ingested robot, so something you've swallowed, on its way around. So it's possible to wait for that to get it to the rough location, and then use the two-dimensional navigation to get to the exact position you need to with the robot.
Other ways of sensing and newer ways of sensing.
So if anyone else has any questions, just pop them in the comments below in the chat. And don't forget, we also have the up, down, left, right navigation.
It should still work right now.
Khan just helped you around the corner there with his finger.
We have one question. I'm just checking.
So a question from Tom. Is it possible to make a second origami robot smaller?
Yeah, of course. Like, as small as you want it to be, because I've got a smaller magnet here, if you can see. So that's the magnet we used on this specific origami robot. However, you can still control this magnet here as well, which is, this is 5 millimeters cube squared. Sorry, this is 5 millimeters, and this is 3 millimeters, I believe. So it depends on whatever size magnet you put in. A smaller origami robot to match would also work. But yeah.
Okay, once we know there's a fault, how do we take care of it, right?
One more question. What is lost in their abilities when making robots small? And if so, is there a way to compensate any loss?
So that's a really good question, Barner. So the amount of magnetism a magnet has is called the magnetic moment, and that's proportional to the volume of a magnet, so how much space it takes up. So as we reduce that, that reduces, if we make it half as long, we make it 1/6 of the volume. So we have 1/6 of the magnet. So that means that the force we're applying with the magnetic field is 1/6 of what it was before if we make the magnet half the size. I hope I've done that. I haven't done the maths right. It's 1/8. But the friction is proportional to the area. So that only quarters when we make it half the size. So we have the issue that we're applying a lot less force, but to only a little bit less resistance from friction. So that makes it harder to make them move, but it does offer some other advantages. So it means they also weigh less, and because they've got that more friction for their weight, it means they don't slide around as much. So it can make them easier to control, but you have to apply more magnetic force to make them move.
One very important thing to also think about the magnet, the robot itself being smaller, is also the detection of where the magnet is. Because if this is inside the body, obviously we need a way to detect where the robot is. We use Hall effect sensors, which measure magnetic field, but it measures the magnetic field coming off from the magnet embedded inside the robot. And a smaller magnet would mean a smaller magnetic field coming from the robot, and therefore it will be harder and harder to detect the smaller you go.
These two areas of research are quite new in soft robotics.
But yeah, thanks for the questions. You can still go on to ask questions or comments.
Already done on them. So from a research point of view, there's not necessarily much more to do.
Right. So how the robots are made? Cameron, do you want to start with yours?
Yes. So I'll talk about how my robot's made first. So as you can see here, we've got a few different materials in this robot. So we've got some plastic, we've got some metal, and we've got metal magnets. So all of these materials, we need to manufacture for those in different ways. So the plastic parts, we buy in sheets of plastic, and we use what's called a laser cutter to make them. So that's a high-power laser that's controlled by a computer to move it around and turn it on and off. And we use that to cut through the plastic and make these shapes. The metal rods, I just cut by hand. And then these plastic parts in the middle, so you can see that, these are quite interesting. So these are 3D printed. So we get a resin that goes hard when it's exposed to UV light. And then we have a machine that selectively exposes UV light to certain areas of the material to cure it in those shapes. And then it does that in lots of layers. So we get these complicated 3D parts, really accurately made from plastic. So that's how my robots are made. And Kwan's going to tell you about...
Right. So this origami robot specifically is made up of 3 layers folded over together. And they can be made with a laser cutter or by hand. And you will have to, of course, fold this. However, this conductive model can also fold itself. And we have other models which can disintegrate in water and also disintegrate in acetone. This model specifically is made up of PVC, a thin transparent sheet, and double-sided tape to hold the first and the second, and also Duraflex, yes. Duraflex at the top, which is the conductive layer, the gold sheet you can see here. And this is folded over together and then folded in the shape of the robot you want to use. Right.
I said
Right. So thank you all for watching. This is the end of our demonstration for this session. When is our next session, Cameron?
So at where the next time is, 5 o'clock, we're going to be demonstrating again. We're going to see all the robots again, and you'll have another opportunity to ask us some interesting questions. So we'll see you all at 5 o'clock.
Bye.
Bye. So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. Right, hi everyone, I'm Cameron and this is my friend Khan.
Hello, I'm Khan, and we are at the Microrobotics lab at the University of Sheffield. What do we do in this lab, Cameron?
So we make micro robots. We focus on robots on sort of the centimetre scale and downwards, with the aim to use those in sort of really inaccessible places, because that's the big advantage of micro robots. So if you have a really small robot, you get it into a lot of places you can't get a larger macro scale robot into. We use magnetic fields to control our micro robots, because if you imagine you send a robot down from a really inaccessible, like down a pipe or behind the sofa or something like that, you can't always get a cable to it to control it with. So we're using magnetic fields to manipulate it and control it. That also means we don't need to put any electronics onto our robot, which means we can make them even smaller by not having to fit those electrical components on.
Right, and that's not having electronics on board for control and having no cables to control it works really well in the favor of medical robotics. So we can have these small micro robots inside the body and control them with the magnetic field we can produce with our coil system. And the main advantage is, compared to using like X-ray radiation, which is harmful to the body in long durations, magnetic fields are not harmful to the body. So we can use magnetic fields to control our robots without any harm to the patients.
So I'm going to demonstrate a robot to you, but first I'm going to show you what this big orange thing in front of us is. So this is what we call the coil system, which Khan mentioned a minute ago. Inside here, we have these electromagnets. So this is a big coil of wire with several hundred lines on it. And with this, we can put electric current through it, either directions, either clockwise or anti-clockwise, using our power supply. And what that does is it lets us make a magnetic field that's either upwards or downwards. And we use those to control our robots. So here I have one of my robots I'm going to demonstrate, and this has on either end some magnets. So it's got one on each end, and they're positioned in opposite directions. One of them's upwards and one of them's downwards, which means when I apply the magnetic field with this coil, it tilts this lever in the middle. So I apply it one way, and it rocks. And then I apply the magnetic field in the opposite direction, and it rocks the other way. So that means then this in the middle rocks back and forth, and then with the ratchet mechanism in the middle, it means these wheels rotate in one direction. So that's a bit like if you're sat on your bike with the pedals and you just pedal forwards a bit and then backwards a bit and then forwards a bit, you'd move forwards sort of stop-start way. You'd keep going forwards. So that's what we're doing with these robots. So there we go. So we're applying a magnetic field with that coil in the middle, and that's driving these robots. And what you can see quite nicely is they work well in the middle where the coil is, but on the edges, away from where the coil is, the robots don't move because there's not the magnetic field to control them. So we'll just demonstrate. There we go. They've stuck together now. So if they get too close, the magnets attract each other and they stick together. But when they're on the road, they run quite nicely. So I'm just going to stop that there and hand over to Khan to demonstrate a second robot to you.
All right. Hello again. So I will be demonstrating the origami robot in a minute after I finish my setting up.
So yeah, I think might go through a little bit more.
Right. Okay. Right. So here you can see is our small origami robot in my hand. And as Cameron mentioned, he was using the coil in the center to control, but we have 4 more coils in each corner, which can create directional magnetic fields that we can use to navigate the magnet around. And sorry, right. And I'm just going to demonstrate what the navigation looks like. There you go. Right.
So as we mentioned, our robots need to go inside the human body. So let's say the robot Jonah just presented, and we first need to shrink it down, right? And then once we place it inside the human body, we can operate with.
As you can see, the robot also can be controlled through the body, inside the body.
In particular, there are 2 examples we like to keep in mind in our lab developments.
Right.
What implants? The first one is low-cap vision, and the second one is
Of course, my hand is a bit too sloped to clearly show the movement, but you get the point. I'm just not good at controlling the robot that well. Anyways, right. So the reason we use origami robots is that they can be folded up into smaller shapes and be placed inside pills, which can be swallowed and reach anywhere within the gastrointestinal tract. And moving on to our next demo, here you can see a small tube magnet that we can control the direction to anywhere within our workspace. And let's imagine our workspace being inside the intestines. And we're trying to reach a position to, for example, collect some samples. And you can see that we can easily navigate through. But one more thing I want to show off.
So again, we have our little actuator.
Right now, you can also control this robot through the live YouTube chat comments. So if you type up, left, right, or down in the comments, you can also control this robot. So if I just type right, it should start moving in a bit, of course, because there's some input lag in the live stream.
Well, first, a lot of experimentation to prove that your robot is safe and can actually safely interact with tissue, but then also
that did something.
clinical trials. Now, what we're trying to do is
Yeah.
more clinical trials. So, in our case, we developed this robotic
Right.
bot
So you should be able to type in the comments as well right now.
tissue and see how our robot implants will interact with
if we go.
the tissue. So in particular, if you think about having a spring with you, like, and you start pulling on this spring, right? It is possible to elongate it at first.
Right. And also, while you can type the commands, you can also ask questions, and we will answer your questions. So if you have any hot takes on microrobots and any thing that's scratching your head, please ask your questions right now, and we will answer them as best as we could.
The same way
Cool.
Right. Can you send more of these robots inside the body at the same time, Cameron?
So that depends on the design of the robot. So something like the Origami robot relies on a very specific orientation of the magnetic field. So if we had multiple of these, they would all face exactly the same way and respond together. So we could maneuver multiple of these together, but they do exactly the same thing. Whereas with the wheeled robot that I demonstrated at the beginning, these rely on a much more simple input magnetic field that either goes straight up or straight down. That means we can have multiple robots on the same plane, like I demonstrated at the beginning, facing in opposite directions and both moving forwards. They'll both start and stop together, but they can go in different directions at the same time. So the behavior is still coupled, so they still respond together, but they're more independent than other designs. So yes, we can use more than one robot at the same time to a point. So if anyone else has any questions, don't forget, pop them in the comments below, and we'll pop them up on screen and answer them for you.
So we are not from what we're trying to.
Right. From which distances can you use this? So
This is a very interesting question. I don't know the answer, so let's test it. So what have we got? So our coils are down here. Where's my? Do I have a ruler somewhere? I tried one earlier. Let's get a ruler to measure the distance with. I definitely have it. We'll measure it using this. So the coil is about 5 centimeters below the surface here. So we know we can definitely use the robot 5 centimeters away from the coil. But we're going to put it on a surface and measure it with something. Oh, here's my ruler. So we can use it 5 centimeters away. So let's go up a bit and try 10. So our robot works 10 centimeters away from the coil. We'll go up again. So we work 15 centimeters. Yeah, we can maneuver our robot 15 centimeters away. We'll go up to 20.
Right, so as I was saying, the problem with
so at 20 centimeters away from the coils, we can just about maneuver our robot. That's using a current of about 6 amps through our magnetic coils. So if we put that current up higher, then we'd be having a stronger magnetic field, which would let us move it further away. The disadvantage of that would be it uses more energy. Also, a lot of that energy goes to heat in our coils. So if we use this coil for a long time with a high current, they start to get hot, and then they don't make a magnetic field in quite the same way they used to when they were cold. So that sort of limits it. So maybe if we put a bigger fan on it, we could use it further away. So thank you for that question, This.
Right. So how the robots are made? Cameron, do you want to start?
I'll start with my robot. So this is the robot I showed at the beginning. As you can see, there's a lot of different materials in it. And different materials we need to manufacture those different ways. So we've got some plastic here, sort of the wheels and the main structure. So we buy that in sheets of a constant thickness and we cut it to shape. And we do that using what's called a laser cutter, where we get a high power laser, control its position with a computer and some motors. And we can use that to cut in very accurately, with a very high precision, to get some nice round wheels and more high precision parts of the shape. In the middle, we've got some very complicated gears and some 3D shapes. I can't cut those out on a flat sheet of material. We need something to do full 3D manufacturing. So we 3D print those from a resin. So we have a machine that puts a layer of resin down and selectively shines a UV light on that resin in certain places to make it go hard. It then puts another layer down and shines the UV light again in different places. So we can get some very complicated 3D structures made to very high precision from that plastic resin. So Carl's going to tell you about his robot now.
Right. So this specific origami robot here is made up of 3 layers folded over together. The first layer being PVC, the third layer being Duraflex, that is the gold conductive material at the top, and double-sided tape to hold the two together, a very strong one at that. And then it can be laser cut into any shape and folded into any origami structure to suit whatever sort of task it needs to do. Of course, you have the magnet that's needed to control the robot itself. And we have different versions of this too. One which can disintegrate inside water and one which can disintegrate inside acetone. We have other models which were used for patching stomach wounds. That one also had a layer of medicine, which would disintegrate to apply the medicine to the wound. But yeah, that's basically it.
And in factories, for example, that's one area where some robots are trying to replace our robots.
Next question. Can a group of origami robots arrange to do specific tasks together for a larger area? Yes. However, so a group of robots coming together would fall into the field of self-assembly, which we are also working on. And we can use magnetic fields to use self-assembly to form larger structures. And the main advantage being in its name, where these are structures that you don't inertly control one by one, but they're interacting with each other is what's called self-assembly. Do you have anything to add to that?
Yes, you can't talk about, it depends what you mean by the question. You can't talk about self-assembly. There's also the field of swarm robotics. Self-assembly is, like Con said, robots joined together. Swarm robotics, they're all behaving differently, but on the same task. So micro robots have a lot of potential for that because they're so small you can get a lot of small space. With regards to the larger area, we are limited by the area that we can control with our magnetic field. So if we had really big coils over a large area, then we could spread them over a large area.
Or coils.
Or many coils. We're limited to just the area we can apply the magnetic field to. So we can, but there's some limitations, like everything in life, really.
There are other areas, for example,
So if anyone else has any questions they'd like to ask, just put them in the comments below, and Khan and I will answer them and let you know.
I didn't take over every
future, we'll definitely see some applications where
Right. Can you navigate in a 3D space?
So my robots that I demonstrated at the beginning with the wheels, they rely on that one coil in the middle, giving a magnetic field that goes either upwards or downwards. So they're, to an extent, limited to be just on one plate. So if you go anywhere in 2D space, if that 2D space has three-dimensional features like a ramp, they can go up that ramp, down the other side, but they can't sort of go anywhere within 3 dimensions. There are some robots you can look at, so moving in liquids and things, so like Hella designs that can sort of hover and go up and down, more like a helicopter, and do sort of true 3-dimensional navigation. So it is something that's being looked at, and people are currently working on being able to do that.
Right. And the origami robot can move up slopes or down and navigate through rubble or anything. But it does this in the 2D plane. It is not tied to this specific plane, but it is tied to this specific area that the coils are aimed towards. So if you had more coils in other directions, you could, or if you had a moving coil system, that would kind of twist around, maybe you could. But you need the source of the magnetic field to be able to provide the 3D space for you to control the magnet in 3D space.
Have our robots.
So thank you for watching our live stream of our demo. And we will be returning when, Cameron?
So at past, we'll be back for the last demo of today. We'll show you all the robots again, and you'll have another opportunity to ask us more questions. So that's at 17:30. We'll be back live on air.
Again, thank you and goodbye.
Most of the questions, so we'll be back.
So I'm Cameron. I'm a PhD student in the Sheffield Microrobotics lab. We make really small robots, sort of on the centimetre scale and smaller, so with the aim of putting them inside the human body to do things like remove batteries that children have swallowed, and do things like solve stomach ulcers by delivering drugs directly to the site of a wound in the stomach. We do that by controlling our robots with magnetic fields, because magnetic fields can pass through the human body without doing any damage. At the festival, we're demonstrating a few different robots that we're controlling with magnetic fields. So they'll be moving around doing different tasks and a surgical procedure with no motor on board, just with the magnetic fields. Hello. So I'm Cameron, and this is my friend Khan.
Hello, I'm Khan, and we are at the Microrobotics lab at the University of Sheffield. What do we do in this lab, Cameron?
So micro robots are really small robots. Our lab, we focus on sort of centimeter scale robots. So the idea of having smaller robots is you can put them in less accessible places. So you're inside pipes, say like collapsed rubble, around the back of the sofa, inside people, things like that. So because they're in these inaccessible places, we can't always access them with a wire to power them and control them. So we're doing that with magnetic fields, because a magnetic field can pass through most materials and still control the robot on the other side. That means we then don't need to put any electronics on our robot, which means we can make it even smaller than it already is, because it's just some magnets and some mechanical parts controlled by the magnetic fields.
And the main advantage of using magnetic fields to power our robots and also navigate is that we don't need any onboard electronics for our small robots, and we don't need any cables to control or power them, which means we can control them wirelessly. And also, magnetic fields can pass through our body, and we can use them in the medical field without any harm to the patient, because unlike X-ray radiation, there is no harm for the patient when magnetic field passes through the body or when they're exposed to a magnetic field in long duration. So it's pretty safe to use in the medical field.
So before I show you our first robot, I'm going to explain to you what this big red thing is. This is what we call a coil system. So inside here, we've got some electromagnets. So these are big coils of wire with several hundred turns on them. And with this, we can put a current through it from our power supply, either clockwise or anti-clockwise. That means that we can have a magnetic field that goes either upwards or downwards, and use that to control our robots. So here's the robot I'm going to show you. At either end of it, we've got some magnets, and they're all orientated in opposite directions. So on one end, they're going upwards, and the other end, they're going downwards. That means that when we apply the magnetic field, the beam in the middle rocks. And then when we reverse the magnetic field, so going up, it now goes down, the beam rocks the other way. And then with a ratchet mechanism, that then rotates the wheels. So it's a bit like if you're sat on your bike and you pedal forwards a little bit and then back a little bit and then forwards again, you'd go forward in sort of a stop-start way. So that's the same as these robots, to get that from that magnetic field to forwards motion. So I'm going to demonstrate that to you now. And I've got 3 of them here. Just turn that on. So now we can see we've got the magnetic field being applied from underneath, and that's making this robot move in the middle here. But what we can see is when it's at the edge here, like this robot, that's away from the magnet, so it's not able to move, and they sort of get stuck where there's no magnetic field. But the one in the middle is quite happily going along, driving. And because it's just going upwards, we can drive in any direction until it crashes with another one, and they get stuck together like that. So I'm just going to turn that off, and then I'm going to hand over to Khan to show you another exciting robot.
Right. So I will be presenting the fingertip-sized origami robot now. It will just require 1 second of setting up. Right. So here's our origami robot that I have mentioned. And you can see that we can control it in any direction we want to. Huh? Yes. As Cameron mentioned, he was using the coil in the center to control an up and down motion. But we have also four more coils in the corners, which can give us directional magnetic fields. And with these mixes of direction, we can control the robot in the direction that we need it to go, such as that.
And then what we can do is we can sort of deflate some more. So in here we've got pulleys in place to remove, cover the bubbles, and so you can
Yeah. And it can also do this through the body. There we go. It's a bit sloped up, so it takes some more effort to go through. My hand will go on the less slope. Will be easy. But basically, it can still work inside the body. Right. And that brings us to our next demo. Here you can see a tiny neodymium magnet that you can control which direction it goes to. Can up, down, left, right. It's pretty responsive. Right. And let's imagine we have used the origami robot inside the body, inside the gastrointestinal tract, and we reach the intestine. And we need to reach this point to, let's say, collect our samples, or that's where we are performing the operation. So you can see that it's pretty easy to navigate in the 3D surface all the way down to our target position. But before we get to the question and answers, I would also like to show one more thing. So right now, in the live YouTube comments below, if you type commands like up, down, left, right, you can also control this robot as well. Do take into account that there's about 10 seconds of delay on YouTube live stream, so I typed right now, and it will take a while until it takes that command. But you can also write the commands too to control the robot. Imagine as if you were if you were performing this operation remotely, you're the surgeon, and you have to perform an operation, but you're not at the location that the surgery is taking place in. So you should be able to control the robot too.
And then you also need a lot of preclinical studies before you can actually implant a robot inside a human body. So what we're trying to do in our lab is taking care, let's say, of all these steps.
Of course, in an actual medical scenario, you will be using something that has less input lag, but that's not our limitation. That's a bit of a limitation of live stream technologies we have now. But anyways, I will also want to move on to the question and answer bit. However, you can still continue to control this robot during this question and answer part. So you can either write your commands or fire away any questions you have in your mind that you want to ask.
And the interaction between the robot and the robot.
So the question is, they are very small. Have you ever lost one, Cameron?
Simon, have I ever lost one? Yes, I've lost one. I lost one this morning, actually. I don't know where it is. If you fancy coming to our lab and having a look around on the floor, that'd be really helpful because I've lost my robot and I want it back. So, yes, I have lost it.
And if you check our vacuum cleaner, I'm pretty sure you can find many of them in the filter somewhere.
Definitely.
The smaller the robot goes, the more chance that we are going to lose one. So, happens.
So if anyone else has any questions, don't forget to put them in the comments below, and we'll pop them up on screen and answer them.
Now, as you can see, the bubbles are forming.
Right.
And
Question from Dana D. What are other applications to apply micro robots / origami robots?
Right. So in our context that we were using, we were talking about how we can place this inside a capsule to reach anywhere within the gastrointestinal tract. However, origami robots themselves can be used in any structure where a smaller structure needs to fold into a bigger one, or a big structure needs to fold into a smaller one. For example, in space, when you fire away, let's say, a satellite that would need to power itself using solar energy, you wouldn't be able to fire away the full solar panels in its form. So there are some which have foldable origami structured solar panels, which can expand to cover a bigger space and end up producing more energy by capturing more light. Do you want to also give examples in the micro robots?
Yeah, so micro robots, lots of things in life are becoming increasingly small. So there's lots of small components and things like your phone, other electronic devices. There's a lot of work in using micro robots to start assembling those micro things. So rather than a big robot to make a little thing, having lots of little robots working together to make a small thing. So things like making adjustable phone lenses, things like that. It's all effectively micro robotics. So there's quite a wide variety of things we can use these micro robots for. So thank you for the question, Don.
that's not what we want, because that's not ideal for
So basically, there are all we do is
So a question, how are you expecting to perform an operation in the future with an origami room? So I think that's what we use, Micah.
Right. So with an origami robot, I've shown you that we can control it in any direction. But there was also one of our devices that can unfold itself. So it would be used in the stomach to patch stomach ulcers. Those are wounds in your stomach, and they can be pretty nasty. So this small robot, origami robot, is very small in its unfolded state, and when it reaches the wound, it kind of folds in like a spiraling structure and opens up into a bigger area, and then sticks onto the wound itself and releases the medicine during its disintegration period, and locally applies the medicine. In other applications, for example, depending on what shape you use for the origami robot, it can perform different tasks. So if you add actuation on top of the navigation, then you would be able to also do other types of surgeries that would need, for example, sample collection or removal of foreign objects like a cancer cell.
actually actuate them because one of our robots at home quite easily.
Right. When do you envisage your robot being tested in an animal or a person?
That's a very good question there, Donna. So we've already done what's called ex vivo testing with one of our robots. So that's vivo means in the body. So ex vivo means outside of the body. So we've done that with some tissue from a dead animal. or something like that. You go to your butcher and buy to do some testing with that. So we know it works. We're a little bit of a way off doing inside animals. That's probably in a couple of years' time. I'd have thought we'd be potentially looking at doing in vivo, so inside a living animal test. And then personally, doing human testing is a lot more challenging. You need to get, for testing on live animals, you need to get ethical approval to make sure you're not going to harm the animal or cause it undue stress, to make sure it's all humane and on the animals. And then you need to take that to an even higher standard before you can test on humans, because we don't want to injure humans testing our robots that are meant to be helping humans. That defeats the whole point. So that's probably sort of 10-year sort of time frame, if not longer.
And this wouldn't be any different to any other type of medicine, for example, that you would have to go through, because you still have to go through clinical trials before it can reach to be used in the public. And some of these clinical trials, of course, involves people using these. So it will be taken, the first group would be an animal group, so it has to be tested on an animal first. Then it will be a group of healthy people, a small size. And if that passes, then you move into the next trial, which is a bigger sample. And then the next trial, which uses patients who do have the targeted disease that needs to be solved. And then if it passes at that point, then it reaches to the public for it to be used.
So if anyone else has any questions, don't forget, put them in the comments below. We'll pop them up on screen and answer them for you. Question from UK-Robotics. Is it possible to make an origami robot at home? Would you like to take this one, Carl?
Yeah, probably. You can make origami at home right now with any piece of paper you have. It's the art of folding. And you can go as complex as you want with it. However, for an origami robot, when we say origami robots, we don't mean just what I'm holding in my hand, because this by itself cannot navigate. It's the origami robot itself and the coil system, which is a system as a whole. So if you have a way of using differently directed magnetic fields, you will need some sort of coil system to control it. But the making of it does not go into too far complexity that it probably can be made. However, it will be very small. We're talking about microrobots. So you will need very precise hands to be doing it at home. So good luck.
If anyone does make a micro robot at home, feel free to put a picture in the comments. We'd love to see them.
Of course, yeah.
All embedded in a software system. And there is one example of sort of Oxford.
Do you want to read the question I'll answer?
So question from Patrick. How do you let these robots enter the human body? I imagine swallowing will be difficult, especially for small children.
Yes, yeah, of course, this is a big issue. So there are standards to what shape and size pills can be. So we chose starting as a starting point, the biggest available pill, which is size 000. Of course, this will be very difficult for a child to swallow. I myself was not able to swallow any sort of pills up until I was maybe 19. So yes, it is very difficult. We are aware. But as we make these robots smaller and smaller, they will be able to put into smaller and smaller pills. So we're reaching that. This is kind of research. So these are the first models. They get better and better in time. So there's not much limiting factor to why we can't go smaller. It's just a matter of testing, trying, further engineering.
integrate
Thank you for that question.
all of this.
Right. Thank you all for watching this stream. This is our final one of the day.
Yeah, thanks for watching. I hope you all enjoyed it. If you've got more questions, still put them in the comments, and maybe we'll try and get to those and answer those in the comment section if you've got anything else you want to ask. I hope you enjoyed the rest of the UK-RAS Network Robotics Festival, and enjoy the other events later in this week. Have a nice evening.
Thank you and goodbye.
Bye.